today we're going to talk about Webassembly, my failed attempt to port it over to Rust. It's ongoing. However, I am going to be sharing with you the experiences that I've had along the way and the things that I've learned, and how Rust and WASM can help us gain performance and get more performant things going on the web. So this is me. This is how I roll now. I'm doing VR now. It's a very new thing for me. I don't have a job anymore. I'm working out of Pioneer Works, doing an artist residency, working with my collaborator and friend Caroline Cinders on a VR project. I generally don't know what I'm doing, especially when I'm doing Unity and like learning C#. Hi Jasmine, where's Jasmine? Doing C#, learning Unity, building worlds in VR. It's good to be out of my comfort zone, to be honest with you, and I think that's maybe something that can be covered in a different talk. But I already kind of feel out of my comfort zone already here upstage, so let's get on with that. So I usually like to open my talks with a little bit of a structure so that you know what to expect. I'm going to open with a little bit about software for art, writing tools as software authors to make art, thinking about the browser as a platform to create interactive experiences, Diffy.js, which is a library that I've been actively working on, performance bottlenecks, and how Rust and WASM can help solve for those things. So let's talk about software art. Procedural thinking and interaction design are two of the main things that make basically computers, has historically made computers really good for making engaging experiences. I'm going to talk a little bit about a few of my favorite artists. Vera Molnar is one of the pioneers of writing software for art from back in the 60s. Computers are amazing at procedurally generated anything, really. They're inherently dumb, but if you give them a beautiful set of instructions, they'll do wonders. A couple of works from Vera Molnar and a few kind of variations on the theme. Manfred Moore is another one of my heroes here with what is the precursor to AxiDraw. Is this called AxiDraw? I don't know. But this is back when you would have to reserve time in universities to go in and hang out in their labs and work with engineers after hours to get whatever design or artistic idea you had come to life. And these are some of the most prominent works of his. These were exhibited in what was at the time a very controversial exhibition called Une esthétique programmée, or a programmed aesthetic back in the 60s in Paris. It caused a lot of outrage amongst the artist community in France. They were like, what the hell is this? Artists should be, basically like sitting there and painting something or making a sculpture. What is this code business doing in the arts? Fast forward, we get to the notion of interactivity and thinking about not only procedurally generating images, but rather thinking about what affordances computers have in creating interactivity. And so this is TextDrain by Camille Utavec. And Camille made this back in the day when, creating interactive experiences like that were not very commonplace. So this is essentially a motion tracked setting where your movements can kind of create contours and visible contours that the computer can track and can respond to. This is now very commonplace, and this was one of the sources of inspiration for writing Diffy. Golan Levin and the work that he's doing at CMU and the Studio for Creative Inquiry has been another source of inspiration. This is Messa di Voce. It's a sound-activated interactive experience by Golan Levin, Zach Lieberman, and collaborators. Again, another kind of affordance in terms of interactivity in computation and creating engaging experiences. That's my friend Jane in the middle. Hi, Jane. This is PoseNet using TensorFlow for doing essentially gesture approximation in the browser. And so you can see the progression of how artists basically started first like going to these labs and universities and talking and working with engineers, moving forward, people creating tools, and then using the browser. This happens in the browser, using the browser as a platform for creating very complex and sophisticated things like that. And so over time, there has been this kind of tradition of creating tools for making art. And it started off with lower level languages, things like processing that is built on top of Java, open frameworks that's built on top of C++, and then P5.js is now one of the most prominent tools for actually teaching creativity and computation, which is entirely built in JavaScript and runs in the browser. And this is the poor man's tool for making stuff, which is Diffie.js. It's not perfect, it has a lot of flaws. I'm going to be talking about those flaws and how I'm working on it, but it's my little not perfect thing, so I care about it. So Diffie.js basically solves for two things: where motion happened and how much motion happened. So essentially, I mean, let me see, okay. So in order to do that, we basically create a grid on the screen, and we start basically comparing two frames to each other, two very high contrast frames to each other, going cell by cell, figuring out what changed and how much changed, and whether or not we want to mark that little cell as changed. And based on that, and I'm going to show you the API in a little bit, we can basically pass a callback function to that, draw things on the screen, make sounds, whatever. So type arrays and array buffers were essentially, were basically essential in creating this. Thinking about linear memory and thinking about how to allocate linear memory in JavaScript to make things more performant was basically one thing that I used to increase performance here. We're gonna get back to array buffers in a little bit when we start talking about Latin and Rust and how that's useful. Bitwise was another kind of technique to increase performance instead of using things off of the math static methods in JavaScript. And so this is essentially the outcome of what the work built with Diffie.js can look like. This is an installation that I built last year. It basically explores video as a byproduct of memory and how that relates to the personal experiences and how over time we go back to memories, we pull them out, we look at them, we put them back again, and how that changes the landscape of what we remember from our past. This is a full-screen Chrome browser projected onto a wall with a simple webcam over there. That was pretty exciting for me at the time to build, and this is what it looks like, one of the artifacts. So people would come into the room and leave, and they would leave basically the state of the software in a different state. This is another example of that last week somebody messaged me on Facebook, said we are graduating from Full Stack Academy, and we built this thing using your library, and nothing makes me happier to hear that from people, because why would you use this library? But thank you also. And so this is maybe my 10th try. I'm not from the States, so I have trouble remembering these. And so if I get these two right, it's because I actually practiced a whole bunch before doing it. But it was really fun. It was really fun to see what people are building. So this is what the API looks like. You pass a bunch of parameters in it. You say what the resolution you want to be, what is the sensitivity that you want to basically guess if things have changed or not, what is the threshold. Debug basically gives you a window to show you the comparison of the two frames. And the callback is basically what happens, where the real stuff happens, where the meat of the things are, and that's basically past a matrix. And so if you were to look at it, it's very simple. You basically have use the getUser media API, and you snap two pictures, you turn that into something very high contrast. You offload the work to the worker, basically the work of going through two images and comparing them together to basically guess if things have changed or not. And this is something I'm going to talk about, and another thing that I use to have some performance improvements. Again, going back to array buffers, this is something that comes up over and over again, because unlike regular arrays in JavaScript that are actually linked lists, array buffers are a block of memory, continuous block of memory, which is essentially what is heap to WASM. And we're going to get to that in a little bit. But even before doing that, this is basically how Diffie.js uses workers to improve performance and to create something like, I don't know, a thread. I'm not really sure. I can't really come up here and talk with confidence about workers are threads, because this is something that I go back and forth and read about it. And I'm like, wait, are they threads though? I can't really tell. But they improve performance, so that's all I care about. So that's great. Okay, so but Diffie doesn't scale really well, because if you increase the size of your essentially matrix, it's going to blow up real fast, and it's going to get really, really, really slow because of the O(n) to the power of 2 thing. And this is something that I always also struggle with talking about, because it's one of those things where you read about it, but if you don't sit in a class and basically like learn about it from a professor, there's a good chance that for the rest of your life you understand what it is, you can talk about it, but you don't know how to pronounce it. But it's like a power of 2 thing, so it's not polynomial. So anyways, I was surfing the webs and I came across this amazing work done on ray tracing in JavaScript and in Webassembly. There's a little demo here. If you're using Webassembly, you can see that the performance goes up to somewhere between 13 and 14 FPS. And if you go to JavaScript, all of a sudden it drops to 1.6, 2.4, so on and so forth. So there's a huge performance gain here. But what are the things that Wasm actually helps you do better in the web? And those are basically the very computationally intensive processes. You can do pretty much anything in Wasm.js. You can access DOM elements, do whatever you are doing using your regular JavaScript and HTML APIs, but should you use it for those things, or should you actually use it for things that require computationally intensive processes? And we're going to get to that in a little bit later. So seeing this, I was like, okay, great. I'm going to try and port Diffie into Rust. I'm going to talk a little bit about why Rust and why not other languages like C or C++. That's a work in progress, but I'm going to walk you through the experiences that I've had and things that I've learned. So what exactly is Webassembly? So is it bytecode? I was talking to a couple of friends of mine right before this, and someone was like, yeah, it's bytecode, and someone was like, yeah, it's machine code. And I was up at 3 a.m. stressing out about what I'm going to say here about, oh, so this is a bytecode, whatever, and then I eventually took it out. But because I don't know if I'm genuinely interested, I'm like, maybe I should just open this to the floor. Because WASM is essentially a portable compilation target, and this is actually running in a virtual machine in the browser, so maybe that's why we can call it a bytecode, but at the same time, it's assembly. But it's assembly that's built for a virtual machine, not an actual CPU with an architecture, which makes it portable. So that makes it machine code, but oh my god, what's happening? So let's just say that it's a binary instruction format. You can use C, C++, and I think that there is some experimental support for this in C# as well to compile it, to compile your code to WebAssembly, and also Haskell using LLVM. Thank you, Aaron, for bringing that up prior to this talk. So it makes it possible for library authors to have interoperability. That's a thing I can never really interrupt. Between JavaScript and WASM, which is fantastic. This is something that didn't exist before. And I'm going to talk a little bit about this later too. And it shares memory with JS. And here we go back to array buffers. So WASM basically uses array buffers as heap to allocate memory. So is it going to kill JS? I hate blog posts like that. They're like, yeah, the new killer thing has arrived, and no longer we're going to have to write JavaScript, this and that. But you know, JavaScript is fantastic. JavaScript is the reason why we're here, hanging out and listening to talks together. And there's no reason why it should go away, because it's been born out of the browsers, and it knows browsers really well. And so why can't we just keep JavaScript the way it is? No, actually keep improving it, but don't throw it away. But use Wasm.js to offload the more computationally intensive stuff. So Wasm is not basically the first, attempt at doing this thing. Asm.js existed before, which is a subset of JavaScript, and it's not something that you right? It's basically using JavaScript as a compile target. And this is something that game developers have used in the past. Speaking of Unity, I think that Unity games also use this technology, historically use this technology to basically target the canvas in HTML5 for web-based games. And then there was this, remember the time where we had Java applets that was like contained in the browser in the middle with like a border, and it just sat there and you did stuff with it and it didn't really like fit in with the rest of the page. So that was the issue there, was that there wasn't really any way for the Java applet to talk to the rest of the browser space outside of it. It existed there, it did its thing, it was a program, it ran you know, on a different Java virtual machine, but it couldn't really talk to the rest of the web page, which was the shortcoming. And so enter WASM. So WASM is more performant because it's typically smaller. It basically has to be decoded. It doesn't have to be parsed and compiled just in time, so on and so forth. No garbage collection is necessary because the languages that you use to use WASM as a compilation target are essentially you know, things that take care of memory management in a different way than garbage collection, like C++ and Rust. WASM right now only supports number data types, which is interesting. It creates limitations that we're going to get to in a little bit, but it's very interesting that this is basically the only thing you have to work with. So why Rust and why not, like, say, C and C++? The fact that it's ushered by Mozilla and the fact that it's being basically built by, with the mentality that, you know, we're going to build this language and we're going to build in native support backend to compile to WASM, basically shows the intent behind you know, the idea that, you know, Rust is going to be this thing, this systems programming language that not only is going to be used for systems programming, but also is natively going to support web as a compile target. Before this, mscripting was being used by C++ developers to target ASM. So starting out with Rust, I'm basically going to walk you through building a very, very simple Rust project and basically moving from there to talking to JavaScript briefly, and then sort of, you know, the process and everything that's involved in the middle. If you start using Rust, you will notice that basically, you know, cargo is their NPM. You can start a new project, and it has two different modes. You can say if it's a library or if it's a binary executable. When you look at the project scaffolding, one thing about Rust that I've noticed as a Rust beginner is that its CLI tool is just fantastic out of the box. It scaffolds the project for you. As soon as you create a project, it creates a source directory, it initializes a Git repository for you, and at the same time, it creates the basic TOML file, which is Tom's obvious, not markup, but minimal language that is used to describe the dependencies for your project. And so it's very useful, and you can do a whole bunch with it. And that's one of the best things about Rust that I've noticed in my short period of time working with it. So this is what cargo looks like, the cargo.toml file looks like. And moving forward, this is the file that basically creates for you the boilerplate. Main function, as is the case with many programming languages, I think maybe excluding JavaScript, is the thing that is going to be called as soon as your program starts running. You basically have a very simple macro that says hello world. This is how you execute stuff. Cargo builds your stuff. Cargo checks your code for compliance, and actually the hints that the compiler gives you is massively helpful, to the point where sometimes I feel ashamed, like, you shouldn't be doing all this work. Thank you so much for doing all this work. It shows you exactly what's going wrong and gives you a whole bunch of very useful feedback about what might be going wrong with your code. But cargo run builds and executes your code. In this case, it basically just puts hello world to standard out and moves on. And if you open your directory structure, now you see that you have your target, and under debug you have basically your binary executable. But how can we move from this to JavaScript? What should happen here? Currently, there needs to be some wrapping code in order for Rust functions and JavaScript functions to be able to talk to each other. Because remember, WASM only supports number types. So we have to be able to describe more than just numbers using the language that we were using to target WASM. And again, I'm going to give this another shot. Interruptibility. How am I doing? Interpretability. I don't know. Okay, so WASM bindgen is a CLI tool that helps you create this glue code, so to speak, and basically create code that you can talk to from JavaScript. And so this is where, in the web world, it gets interesting. You basically add the dependency, WASM bindgen. You're going to annotate your code using WASM bindgen to tell your Rust code that you need this code to be wrapped for use in WASM and JavaScript. All you need to build this is basically a very simple shell script that targets WASM as a compilation target and uses WASM bindgen to then process that compiled target to create the glue wrapper code that allows you to use WASM in JavaScript and call essentially Rust functions from JavaScript, which we will see in a minute. npm install and npm run serve are very simple. Actually, the only things that we have here is Webpack, and Webpack 4 onwards natively supports WASM, so we don't even need special loaders for WASM, which is terrific. You don't even have to think twice about it. And the fact that we have two languages with two separate ecosystems sitting side by side, it's just so neat to me. That you can have your source files, you can have your index.js, and you can have your Rust file all in one project. Everything's very clear. And it just seems like, again, to go back to the idea of why Rust, it's built with the web in mind as a first-class citizen. That didn't actually come out right. All citizens should be first-class citizens. But I mean, this is, in my head, like how, like how objects are first-class citizens in JavaScript, so on and so forth. I want to blame Doug Crockford for this because I feel like that was the first time that I read that thing in that book, but I also learned a whole bunch from him, so I'm not going to blame him. Anyways, they live side by side. It's very happy. It's amazing. Working with it is very seamless. And if you want to build something that is going to target WASM, you're essentially going to want to write this as a library, not as an executable. So basically here, you are basically saying that I want to import the WASM bindgen crate, which is the package, which is basically package in JavaScript land. And you start annotating things, like for instance, I want to import this external function called alert from JavaScript, and I want to annotate this using an attribute called WASM bindgen, and we're going to see how WASM bindgen basically wraps this code in a way that it can be called, from both sides. And we expose one function called greet, which takes a reference to a string and basically uses a very simple macro to say hello and the name. The package.json file, like I said, very, very simple. There's not much to it, just Webpack and Webpack dev server. And the Webpack config is the most delightful part because you don't really have to do anything. It's basically one of the most minimal Webpack configs that I work with. And Webpack configs are basically like the reason why I'm traumatized when I start new projects. However, the defaults have been improving so much that at this point it's much easier than before. And on the index.js side, all you need to do is essentially import your WASM greet module. And notice that right now, for some reason that I'm not entirely sure of, we have to use asynchronous imports. Otherwise you could have just done like, import greet from WASM. And so, you basically import it and you can essentially very seamlessly call a function signature called greet in Rust that we wrote in Rust and basically executed from within JavaScript, which is pretty magical. And so if you look at the JavaScript file that WASM bindgen has created for us, talking about the wrappers, there are two very interesting functions in here. And I'm just immensely thankful to Lynn Clark for being so amazing in teaching all these concepts and making all this stuff so accessible. She was a person who, in a blog post, brought my attention to okay, so if we have only numbers, how are we going to be able to describe other types? And the way you basically do that is you essentially have a pointer and a length. So using that, you can pretty much describe anything. If you think about your heap and being described as an array buffer, which is a shared memory between JavaScript and WASM, what you can't do in WASM is say, I have a string or I have an object. What you can do, however, is you can say, here's where that thing lives and here how long that thing is. And so using that, you can essentially describe other types and get coding without having to think about, oh, my compilation target only supports numbers. So that's the glue code. If you fire up the server, you basically see the magic of, oh, I wrote a very simple function in Rust, and now I'm calling it from JavaScript. So this is a very quick rundown of how these things work. So should we use WASM for everything? We can do it. We can access DOM. We can draw things to the screen. We can essentially write Rust code to use the Web Audio API and do whatever we want. But at least my thinking is that JavaScript has been primed, and the tooling around it, the frameworks around it have been primed to solve commonplace problems in the web. And a lot of amazing patterns have been established for doing these things, and a lot of community standards have been built around it, a lot of consensus has been built around it. So there's no reason why we should shy away from just using JavaScript to do this JavaScript-y stuff that we want to do. But if we want to get stuff that's performant and closer to the metal, then that's potentially a place that we can use another language and use WASM as compile target to go about basically writing our software. Yeah, that's all I have for today. Thank you.